So yes, my excuse for claiming to be in Russia is that a week ago I upgraded my laptop, so I failed to rebuild my slides with the proper headline. Actually the title slide came out okay, and nothing else did, basically. So we are still in Dallas, I believe. Even, I didn't just turn this whole room into a TARDIS and send you off to Russia. That could have been fun, but we didn't do that. Okay, so as Chris said, my name is Magnus Hagander. I'm on the Postgres core team, one of the developers and committers. I do a lot of work for Postgres Europe, along with things like organizing conferences like this one, but over in Europe. When I don't work on the community Postgres, I work for a company called Red Pill Pro, which is focused in the Scandinavian region. I'm out of Stockholm in Sweden myself, where I work basically with what we call infrastructure services, which is everything from the bare metal up to approximately the database or maybe the application server, but not actual application development, things like that. We have other people doing that. And of course, for obvious reasons, my main focus is on database services. Now this talk is based on basically a client story that we did about a year ago, I think in the end, where we had to step in and try to solve a problem for a client. And obviously I got called in once they realized that maybe we can have the database help us with this, because it turned out the problem was harder than they initially thought when they said, oh yeah, we can fix this. This is not a problem. So we're going to talk about a TARDIS for your ORM. Everyone knows what a TARDIS is, right? Does anyone not know what a TARDIS is? Okay, good. I think that's the first time that everyone knew what it is. Everybody knows that this is a TARDIS, right? Now we're not going to talk about exactly that type of TARDIS. Instead, we're going to talk about what we actually did and what we ended up doing to solve this problem, which is basically application level time travel. We had actually, how many of you were around back in the days when Postgres had built-in time travel? Not even Robert? Yeah, Robert-ish, a little bit. Nobody else? Yeah, or one more? Okay, so Postgres used to have time travel, which basically meant you could query your database at whatever state it had ever been in at any point before. The implementation was fairly similar to never running vacuum on your database today, except we also had an interface to query the data. Obviously, that was not awesome for performance, so it was removed along 7.1 or something like that. It was removed from Postgres to have it on everything. If I'm not mistaken, I think at the time we couldn't turn it off either. It was just always there, so it was always slow. But there are some times when we actually end up needing this. So let me just take a step back and start with the actual requirements that the client in this case came to us and said, we may have told our people that this is a simple problem to fix, and maybe it isn't. So you guys need to help us to try to get this done. So the requirements that we had was basically, this was an existing application. It was a fairly large application, or rather there were a couple of different applications all working on the same data set. And one of the core requirements were you cannot change the data model. Or if you have to change the data model, you can at least not change the data model by much. We need to minimize any changes to the data model. There is a lot of legacy code running on this. There is a lot of legacy data that we don't want to touch. We want it to just magically work. And the thing is, the data here contains both very detailed data and very much sort of overview aggregated statistical data. Among the detailed data is very sensitive personal information about people. And then, of course, it's aggregated based on geographical locations, based on other sensitive attributes on these people, and things like that, that are what's bringing sort of the content to the database. Now, the application, as it is, has a couple of things to know. Data is mostly loaded in batches, coming from other systems, to sort of as a central point for those. There are no live systems feeding sort of input from other systems. There are, however, manual corrections that are made by people. So you get batch loading, and then people look them over and go like, oh, this batch had incorrect data in it. So they go fix that data. This is done manually, and this part of the system does not have a large number of users. In particular, it does not have a very high number of concurrent users. And most of their time is spent reading data, not updating it. So the number of sort of updates are of low concurrency throughout the system in general, whereas the number of reads are much bigger. There are a lot of large aggregate reports that run that take, look at hundreds of thousands or millions or tens of millions of rows and producing a nice little graph with things on a report that people can show. There are also smaller detailed reports that are running, and there are reports running down to the level that the reports include some of this very sensitive personal data, which is some of the reasons that these requirements show up. Now, so far, listening to a description of an application like that, that's all pretty standard, right? I'm sure we've all either built or been exposed to applications that have, this type of requirements. And those are pretty good. But this is the application that already existed. Now, the requirement they had trouble with, one of the requirements they had trouble with fulfilling was they also need to be able to, at any given point in time, reproduce any previously generated incorrect report. So if someone ran a report a year ago, and since then people have corrected the data in the system because of these manual corrections, they needed to be able to reproduce that report as it looked a year ago. And they needed to also be able to run the similar report with the corrected data, obviously, and then in some points needed to diff those two to each other at the application level. But in particular, they needed to reproduce the reports that were incorrect, or reproduce another report running on the same incorrect data. They also needed to be able to identify which reports had been made containing a specific person far in the past. And the idea here is basically if somebody runs a report and then leaks that data, you should be able to track back which reports contain this piece of sensitive information that might have been leaked. Now, luckily for us, this requirement in particular has basically no performance requirements at all. It can take a week to run this. That's fine. The hope is that this will never be needed. Whereas this part, they run daily, right, on different things, because that's the job of the statisticians who run these things, is particularly to look at how these things have changed, how the data has corrected over the years, and things like that. So luckily, not performance sensitive, but it's still there. And those were the main sort of data level or business level requirements. Then we also need to do this while maintaining application flexibility on the technical side, which means we need the current application to run just fine on this, preferably with no changes. And this includes they have people writing not direct SQL queries and not actually direct HQL either, but very close. They have a little query generator where they can drag and drop and create their own joins and things. So this is not a set of predefined reports. These are more or less arbitrary SQL queries that we need to be able to run against the old data, one way or another. And we'd like to do this without changing a single line of code in the application. Obviously, we're not going to be able to do this with not a single line of code changed. But we try to minimize it. Part of it is this is a large application developed by multiple teams. It's been around for a long time. I'm sure there was nobody who actually knew everything about all of it. That's usually the case after, 15 minutes after you've started. Nobody really knows the whole thing. But it's been around for a while. So we need to at least minimize these changes. Get them down as low as possible. It's not going to be zero, but the goal is to keep them as small as possible so that we'll ever have a chance of finishing this project, right? The application that we have, it's a JBoss Hibernate application. It does exist. It's all on, I don't actually remember which version of JBoss, but it was back when it was called JBoss and not Wildfly, but it's not ancient. So it's a decent version of JBoss. Lucky for us, their data was in Postgres, because that gave us the ability to do a lot of things at a layer below the application so we don't have to modify everything that's in the application. Now, one of the important things that we got out of the fact that this was a JBoss Hibernate application is that it has a simple schema, because it's an ORM-generated schema. They tend to be simple, right? They don't do any fancy things. There were a lot of tables across this application, but they were all pretty simple tables. There were no sort of fancy constructs. There were basically no tables. There were unique keys. There were foreign keys. I don't think there was a single trigger in the system, because ORM applications tend not to have a lot of triggers. No sort of recursive relationships or any of those things that are hard to model in ORMs. So they just didn't do that. This made our life a lot easier. There are some other properties on the schema that we took advantage of and said, okay, so can you as the application guarantee that we'll stay in this scenario? One of them is that all the tables are actually in the public schema. Database does not make use of multiple schemas, so we can use multiple schemas and trick the application using that. Also, every single table has an ID column with a serial and a surrogate key and a primary key index on it. Because it's an ORM, it's Hibernate, it likes to do that. We can, in general, argue whether, should all tables have one of those? In a general database, maybe they shouldn't. In this case, it made our life a lot easier. So we just said, okay, let's make a requirement that if we add any tables in the future, they have to also have one of these ID columns. And the application developers in this case were all, well, of course, they get that automatically. This is not a problem. And then there are very few schema changes in the application. There are a lot of data changes, but actual schema changes happen infrequently. To the point that we could just say, okay, so you can no longer use the Hibernate functionality to auto-generate the schema directly in the database. Schema changes will be handled manually. Now, you can use Hibernate to generate an SQL script, but you will then have a DBA actually process the changes so that we can apply our database magic onto these changes at each individual time. And they're looking at, schema changes happens twice a year, this number of changes. So it's very easy. Okay, so how do we solve this problem? Step one is fairly simple. We obviously need to keep all our old data around. If we want to be able to reproduce a report based on old data, we can't delete the old data. We can't change the old data. We need to keep it around there. And we need to keep track of when every single piece of data was actually what we at the time thought was correct. So that when we correct something, we sort of stamp a validity saying, okay, the old version existed until now. But now we have a new version that has our changes in it. And I'm sure most people in here, actually, let me do it. So how many in here would consider themselves primarily like a developer rather than DBA? And DBA rather than developer? Okay, so sort of halfway. Both DBA and developer? Interesting, I thought I'd see even more people on that. So, but I'm sure everyone has run into the concept of having history tables in your database, right? For auditing or for something else. And that's a good way of keeping track of these things, right? We have a history table that keeps all our old data in it. Who has ever used a range type in Postgres? Wow, that's not a lot of you. So who knows about them but have never used them? I don't believe you, Robert. Okay, that's a few more. Anyway. The idea is we combine these two. We use this range type and assign every row of every table a validity period that says this row in this version was only valid for a specific period of time. And to do this, we basically, for every single table, we create a history table. Obviously, we wrote a short 10-line script that would do this automatically. The idea is for every table, we do a create table, and we have a schema called history, that we put all the history tables in. We give the table the same name as it would have in the public schema. And we say like public.table1, which will make this table have the same columns and constraints as that one. And then we just add a valid range, TZ range, which is the timestamp with time zone range. The underscore at the beginning in there is just to make sure that it doesn't conflict if there happened to be a column called valid range, which I think was present in one table. And there were no columns prefixed with an underscore. This will recreate or create a table that looks the same with just one extra column. A quick recap for those of you who may not have used range types or who knew about them but haven't seen them in reality. So this is an example of the valid range column for this, for each row. This is a TSTZ range on each one of them, whereas the first one, just that the range starts at 2014-02-17, 1449-52, and is valid until the same day at 1450-06. Then we have the second one that has starts to be valid at 1450-06 and is valid until infinity. Now, one important thing to know about the range type is you'll notice that the start of it has a square bracket, and this one has a regular one. That means that one end, the square bracket, means that this value here is inclusive. This value here is exclusive. So by putting exactly the same value up here and down there, making this one exclusive and making this one inclusive, means there is no gap between them, and there is also no overlap between them. If we were using two exclusive ranges, we'd have to know exactly what happens to be the granularity of the numbers that we store to make sure that there's no gap. Because if there is a gap anywhere, we're going to have a big problem. And if there's an overlap anywhere, we're going to have an even bigger problem, right? Because then we'll have two versions of the same row, because we assign this to every version of the row, saying this version is valid for this long. If we have an overlapping time, that would mean that an updated version of the row would be valid at the same time as the version that it replaced. And that would be bad, as a general rule. And of course, the last one here, infinity here is just a specific value for timestamps that is basically it's valid until forever. So when we've done this, we create what is known as an exclusion constraint on this table to make sure that we can have no overlapping values. An exclusion constraint in Postgres is similar to a unique constraint, except a unique constraint ensures that there are no equal values in a column, and an exclusion constraint ensures there are no overlapping values in a column. Now, for a lot of data types, overlapping values make no sense. Like, what's an overlapping integer? Doesn't really make sense. But for a range type, overlapping values makes a lot of sense. Basically, it says we can have no overlapping range values. And as you write it here, you see we say alter table for each table. We add the table 1 exclusion, exclude using gist. That's just the syntax we use for exclusion constraints. And then we say ID with equals, comma, valid range with double ampersand. That means for each ID value, there can be no overlapping time ranges. It means that every individual row gets its own set of valid times. And this is where we get to that requirement that there has to be an ID column. Because this one is not going to work unless we have a primary key. It could work if the column had a different name. It's just it would be much more work to generate all of these schemas and in the future to generate the queries. But we need a primary key. So we say for each primary key, there can be no overlapping validity range. Okay, that part's pretty simple. Probably fairly similar. Most of you, when you've worked with history tables, you've had a table and you may have just had a timestamp saying when that version was updated. The important thing here is we assign both the start and the end time of when this row is available, because that'll make querying this data much easier. And once we have our history table, or a history table for all of them, we just need a trigger. So we assign a trigger to every table. That is a create trigger, table 1 history, before insert or update or delete, so we track all of them. On public.table1, for each row, execute the procedure history.logTableTrigger. So we're going to have one function that takes care of all the history management, and we're going to stick that one in this logTableTrigger function. We don't track truncate, for example. We just don't allow truncate. No user has permissions for truncate. And yes, if you're a super user, you can bypass anything anyway, so it's nothing much to do there. But we don't allow truncates. That would make things way too complicated. And of course, they're also never actually deleting that much data. The whole point is we're keeping the old data around. So basically what we get with this is we have in the public schema, we have the current data. At any given time, the current version of a row or the current set of data is in public. And history contains all the historic data. So what the trigger needs to do is basically figure out when things change in public, reflect that in history. We don't want the application to do that. That would not fulfill this whole minimum changes. So we're going to do that in the trigger. A slightly shortened version of how we do these triggers. This is PGSQL, obviously. First thing we do is, so if tgop is a magic variable that gets set to what fired this trigger. So we're saying if what fired it was an insert, then we're both going to insert the data into public, of course, but then we're also going to generate a row in this history schema. So we insert into history dot, and then we have TG rel name, which is going to be the name of the table, also magically filled in by Postgres. So we insert into the history table with the same name, select $1.* using new, meaning we select all the columns that were just updated. And then we add one column at the end, which is the result of the TSTZ range. So we create the range for this one. We indicate that this version of the row is going to be visible from right now, which would be now, until infinity. But that's normal. I just inserted into a table. Of course, I inserted it, it's there. For now, it's, as far as I know at this point, it's going to be valid until infinity, or hard drive crash. And then at the end, we say it's going to be inclusive at the beginning, exclusive at the end. Inclusive, exclusive makes no real sense for infinity. That's sort of in the definition of infinity, but we'll see how that one becomes important later. So we run that insert, and then we say return new, which means we allow the system to also insert into the table in public. So we got the one copied. Now that's the easiest one. If what we're catching is an update, and yes, I'm sorry, this is still a slightly simplified version. It is actually a bit longer. If what we're catching is an update, what we're going to do first here is we're opening a cursor, selecting the valid range from our own history table, which we get by history dot and our TGRL name, where ID equals $1. So this is the second place where we're requiring this ID column to exist and to be the primary key. So we're getting the history value for the same ID using new.id. This is the updated row per the trigger. And then we say order by valid range descending limit 1. Means we're getting the latest version that's in the history table. And then we do it for update to make sure that nobody else goes in here. And this is where we take advantage of the fact that we actually have fairly low concurrency. So we can afford doing a lot of select for updates on these things. And we are going to be doing updates on this one, we know that. So the next thing we check on this is actually, if we create, in this case we say, is this range type constructed by this empty? That means, is the start and the finish the same thing? And we create the range type of the lower value of the one that came up from here, and right now. What that basically means is, does the currently last version end its validity at now? What that means, there are two possible scenarios. Either somebody updated it right now, at the same time, or somebody updated it in the same transaction. Now, we can handle both of them, but what we're doing easily here is we're just saying, if last XID is not the same as TXID current, meaning if this last row was not updated by us, then we're just going to raise an exception. We basically say, if somebody else updated it within the same microsecond, we're going to give you an error, and you're going to have to redo that from the application. As far as I know, I haven't talked to these guys in a while, but at the time, this never happened in reality. We managed to provoke it in testing, but we never managed to see it happen in reality, which is why we felt it's okay to just raise an exception. However, in the second scenario, we say this row was already updated by somebody else in our own transaction. We're just going to go in and we're going to delete the previous update because our update is going to overwrite it, and we know that we're in the same transaction. So the previous one will, for any sort of external visibility's sake, never have existed. So basically, we delete from history where current of the one up here. So if we have multiple updates, and this is something that we initially did not have this requirement, because the application developers would say, we never update the same row twice in the same transaction. Yeah, that was not true. That happened many, many, many times. I think we got 5 seconds into the first test run before we hit that. So that's where that part is. Now, what we're mostly going to do is we're going to end up in this else blocks, which is, okay, so we have not already updated this row. In that case, we say execute, we update the history table, and we're going to have here where current of this query, so we're going to update the last row for our primary key in the history table. We're going to change the valid range. Now, the last row is going to be valid from some time until infinity, right? That's what happened when we inserted it. Well, we're going to change it so that it's valid still from the same time which is what we get by, sorry, we're up there, which is what we get by this one, $1. We copy that. This is lower TT, so we're copying the lower value of the previous range type, same start point, and we change it to now. So the previous version of this row is no longer valid until infinity, it is valid until now, because we're updating it. And this is where it becomes really important that we set this correct, inclusive at the beginning and exclusive at the end. So it's valid up to now, but it's not valid including now. And once we've dealt with these updates, we just go in and say, okay, but I've actually updated it, so I need to record this new version as well, which I do with the insert down here, insert into history. This is the same one as we did for a new row. We insert it, it's valid from now until infinity. So when we've done the update, the old version is going to be valid up till now. The new version is going to be valid from now and forward, which makes sense. And then we do a return new so that we allow the update to happen in the main table in public. And the final operation that we support in the trigger is delete. So deletes are very similar to updates. So we make the same things. We get the last change up here, order by valid range, limit 1 for update. And we fetch it in there. We check if this row has already been updated, but is now deleted. In that case, we again get rid of the previous update because we just deleted that update within the same transaction, so it's no longer interesting. That is exactly the same change. And what we do then is a deleted row means we go back to the latest version that we had in the history, we update the validity time to say it's valid until now, exclusive, on that row. We don't add a new row to the history table because we deleted the row, it no longer exists. So now we will have a series of values saying, okay, it's valid from this time until this time. And then a different version is valid from this time until this time. And at the end, there's nothing that's valid until infinity. So if we were to look for whatever is valid tomorrow, there's just no row there. So we don't actually delete the old data. That would break everything. We just flip the validity period on the very last row. If this was ever only one row, there's still going to be one row in the history table with one start and one end time. And then we say return old, because when it's a delete trigger, you have to return old instead of return new, because new is empty. There is no new version of the row when you deleted it. And that's, again, just to tell Postgres that you may go ahead and delete the row from the table in public. You can also return null, in which case it will just leave the row in public and your data will be beautifully corrupt. So by doing this, we're now tracking the data across time. Of course, we also need to access this data, right? And it turns out, again, with the range type, this makes it really easy. For every query, we just need to specify which of the versions we're interested in. So in this case, for example, I can do a select ID and columns A, B, and C from my history.table1, where ID equals 42, and I add the and valid range. And this is the containment operator. And we give it a timestamp saying, so give me every row for this ID where this timestamp is contained within validity range. And given the exclusion constraint, we know that this will only be one row per ID. It can be one row or it can be 0 rows if it's been deleted at this time, or if it wasn't created yet at this time, but we can never get more than one row. And this thing will use just index. The exclusion constraint will create an index, so make this an indexable operator, and it runs pretty fast. And by doing this, it's actually pretty simple. And this works really well. We just, again, have to add the valid range. And if we join 10 tables, we just have to add the valid range 10 times. Not that hard, right? Except it doesn't really follow this minimum modification thing, because we have to modify every single query in the system, including the manually typed in ones. So that's not really going to work. When you start looking at joins, it does work really well, as long as you remember to add the valid range check to every single table in the query that you're joining or subquerying or whatever you're doing to. It actually is surprisingly fast, given that even joining fairly large tables with this range thing in it. But it's not minimum modifications. So we need to do something else to make the application see this thing more transparently. So now is where we get to the TARDIS point, right? I should have just called the schema TARDIS, but I didn't. So we create a new schema called time travel, which we will use to trick our ORM. And what we're going to fill this new time travel schema with is views that are auto-generated, and that look like this. So we're creating a view for table 1, and we're going to create a view for table 2 and a view for table 3, etc. That is going to select every single column in the table, except for valid range. So we can't do select star. If we do, we're going to suddenly get an extra column back, and that's going to confuse the ORM or any other layer. It might pop up into the report. We'd rather not have it do that. And this one just does select all these columns from history.table1 and adds the valid range where clause. So where valid range matches, and then we're going to use the current setting function. Current setting is just a function in Postgres that is normally used to get the value of a configuration parameter. So you can say select current setting of workmem or shared buffers or something like that. But you can also create your own settings. Originally, this is intended for like you have an extension or something. You want to put it there, but there's nothing limiting you from doing it yourself. In old versions of Postgres, I don't actually remember exactly when this changed, but you had to register your custom GUCs. So you would have to write an extension that only told Postgres, I have more parameters. But you don't even need that anymore. You can just create your own settings. So we're just saying, selected where current setting, we get the history.timestamp, and we cast it to a timestamp with time zone, because all settings in Postgres are going to come back as a string. We don't have timestamp time zone, like the current setting will always return a string or a text. So we cast that to timestamp with time zone, and we add the validity. So that means at this point we have a single setting. As long as we query the views that are in the time travel schema, we can set this time value to any point, and it will affect all the views in there because they're all getting the same setting back. And if we're joining across them, we now join across the views, and it will automatically add this to all the different parts of our join. So we have a single setting that actually controls the current time. And the next thing we do is we exploit the schema search order, which is, again, now is where we come back to the fact that we only had one schema. The application only knew about one schema. The application doesn't know about schemas at all. I think Hibernate does know about schemas if you wanted to, but in this application, they didn't. So all the queries that came in from the application were coming in without the schema qualifier. They were just select star from table 1. They were not select star from public.table1. So that means that we can just tweak the search path. So in this simple example here, if I say, set search path equals time travel, that means it's going to search for the objects in time travel. If it doesn't find them there, it's going to go look in PG catalog, which we don't really care about. And then we say set history.timestamp and give it a timestamp. And whenever we query a table at this point, it's going to give us, when I do select star from table 1, it's going to go back to the view, because the view is in time travel. It's going to extract this timestamp, and it's automatically going to add the where clause, saying, show me the version that was valid on March 7th at 1432. And if I want to do full time travel, I just change my timestamp here. So this is the same query that I just had. It returns 42, 1, 2, 3. But if I change it to 1429, see this one was at 1432. I move back in time, 3 minutes, run the same query. I got the value as it was before that.
So your query just sets the property instead of passing the value.
Exactly. So the query, what I do is I set history.timestamp, then I don't have to change the query. And that's the property that we want to look for, right? If we don't have to change the query, that means we don't have to change every single point in the application where we make a query. It becomes completely transparent to the application. So what we have at this point is basically automatic time travel, right? Once you've managed to inject the search path and the setting of history.timestamp, time travel will just follow that, completely automatic and transparent to the application. So what we need is to inject this. Now, how we actually do that is obviously the main properties of this will work for any application framework. It doesn't have to be an ORM, as long as you can abide by those requirements of having the ID column and those things. So it's going to exactly how you do it. We experimented with a bunch of different ways of doing it. You can do driver level injection. You can have a query wrapper. Like every query has to call this one function and just add a parameter, and then it'll deal for you. We had just a separate function call for a while. What we ended up mainly going for in this particular application, since it's a JBoss application, is to use driver level injection. And we basically wrote our own JDBC driver. That sounds like, wow, that's not a small change. But of course, we didn't actually write our own JDBC driver. We inherited from the Postgres driver and just overrode a few small things. Now, I didn't write the Java part, so I can't explain all of it. But basically, we inherited from the org.postgres.driver. And there is something here like if connection isn't null. Yeah, so it calls the super to get a connection. Whenever the application tries to connect, it will first grab the connection, and then it'll call its own function called inject time travel. And then there is a setting sort of bubbling down through the application somewhere that tells it whether it should put a time travel in there and what the time is. Exactly where that is done will obviously depend entirely on how the application is written and how it works. In our case, I think what they implemented basically, it's a web application, obviously, since it's JBoss. So I think they just stored the time travel value in the session and just extracted it from the session. If it was there, it would throw in the set search path and set history.timestamp whenever you connect it. But that's going to very much depend on how the application works. In a lot of cases, you might actually accept making a few more changes to the application to make a bit more streamlined integration. Sometimes the requirements really are touch as little as possible, and then just injecting it at an early point will definitely help. There are a few things that are worth thinking about. For example, don't forget to reset this thing when you're using a connection pool. Really, really funny things happen in your application when somebody else picks up a connection that has time traveled back in time, and then they run their queries. Or they run their queries, they return it to the connection pool, they come back and get another connection with a different time travel value. Those reports look really funny. And we all know they make entire episodes of TV shows around those things happening, right? When you have a real TARDIS. The other thing that we did as a pure performance enhancement is that we kept the current version of all the data in public, because most queries still had no time travel, so we let them query public. Now, we could have just sent every single query into the history schema and just said time travel to now. That works fine. But obviously, if you're querying the current data, querying public is going to be faster. And again, the queries against old data were, at least to me, surprisingly fast. The application worked perfectly fine. Nobody ever said anything about performance, which is what we sort of expected. But we still optimized by using public schema for current data. But we didn't even need to store it. Public could also just be a view that always queried for now, for example. It's all doable. We decided not to do that as a performance enhancement. The other thing that we had to do around performance is, obviously, this thing added one index, right, on ID and validity time. For a few cases, and that's the part that we had to do manually, we had to create indexes on the history tables as well. When they were running searches on them, we couldn't have just the validity period. We needed some other things indexed as well. We decided explicitly not to copy every single index into the history, because they would be different kinds of queries. Some of those indexes would make no sense when you were querying historical data. So we just accepted that basically we ran performance tests, say, oh, this query is going to need an index, and created the index for that one. As I'm sure you've all done with sort of any application. So we did need a few indexes like that. So with that, there's only one actual requirement left. How did we identify which reports contained a specific query? A specific person. Reports run back in time. Does anyone have a good suggestion for how would you solve this problem? Any reports that ran last year that returned data about, Robert? Who ran them and what did they return? Any good suggestions for solving that problem?
Record the query that issued the report.
Record the query that issued the report. That's one way of doing it. It's kind of brute force. But yeah, that's actually what we ended up doing. Because we couldn't figure out the better way to do it. We were experimenting. There was actually one other requirement. We were not allowed to deploy binary code on the database server. Because we were looking at maybe we could do something like inject an extension to trap this data and log it in a slightly smarter way. But we were not allowed to deploy binaries on the database server. So we could use PLPGSQL, and the binaries for PLPGSQL are installed by default. But we couldn't write our own. So basically, what we did was we logged the entire queries. And then to figure out what it was, we just reran the reports with time travel. So combining these two. Now we added, like for known reports, because the majority of all the reports and the majority of all the queries would not look at personal data. They would look at the aggregate things. So we could filter those pretty quickly, and we had a few of the reports that people just said, these are the most likely ones that we're ever going to need. So we had a small script that would just like pre-filter for those to find them. And then we reran the reports over and over and over again to figure out if somebody had leaked data about Robert. It is very, very slow, but it does work. And again, the fact that they said, it doesn't really matter. Like if we have to do this, it doesn't really matter if it takes a week. It's going to take a lot more than a week to get the court order to be allowed to do the search anyway. So yeah, that part is not quite as slick as the time travel part. But the time travel part is obviously a requirement for this to work. Because when you run this thing, you also need to make sure that you're looking at the version of the data that was current at the time. Otherwise, you don't know whether the record would have been returned or not. So it's not a very efficient way of doing it, but it does work. Whereas the time travel part is actually quite efficient for solving that side of the problem. So we'll have to figure out a way to do this one better as well. We just haven't figured that out yet. Another word of warning about this is ORM level cache. We ran into that problem with one of the applications as well, where they were basically having an entity cache in the Java layer. That is even more confusing than handing back and forth connections with different time travels. Because now individual values would be cached based on different times. And yeah, that didn't work out too well. The thing is, you can still obviously use ORM level cache. I think we ended up not actually doing it, but we figured out how to do it if you want. The only thing is you need to add the time travel value to the hash key so that for every entity you cache it once per time you've looked at it for. So the cache doesn't consider them being the same entity. So it's not that you can't make that work. It's just that the cache that you put at the application layer needs to be aware that there is time travel happening underneath it. So that's something that we couldn't fully trick out. And in our case, we ended up just turning it off because it was fast enough anyway. But it is certainly doable. So some of the conclusions that we drew out of this was, the first one is really, it's amazing how many cool things you can do with range types in Postgres. For all those of you who didn't put up your hand that you've used them, you should look at using them. I'm sure you can find a project somewhere in your organization that could benefit from it.
You have an unbounded range and everything, and nothing overlaps. You always have a point. Everything always resolves to.
Yeah. If you can have, if it goes from minus infinity on one row to plus infinity on the other, you can just pick your point along this range at any given. Yeah.
Yeah, that's pretty slick. Have you generalized this, or was it just specific to the
It was reasonably generalized in that we had a script that would just enumerate the database and punch the data out.
But it was still private to the customer.
It is private to the customer.
Have you thought about doing something like this with logical encoding? Back end just catching it?
Yes. This was done before we had logical encoding. This is deployed on 9.3. But we were certainly looking at, in particular, whether we could do something about the auditing side of things. Unfortunately, logical decoding still will not track selects.
Right, that's the problem.
But that's where I think we actually had a small thing where we had, before we realized the requirement also that we couldn't deploy binaries on the server, where we'd have a small extension that would trap the selects and feed them into logical decoding, sort of by faking it. But yeah, that turned out to not do. So the other point of this is, again, ORMs, we can, as DBAs or database people, you tend to, most database people dislike ORMs because they're so simplistic and they generate stupid queries and stupid schemas. So we can actually use that to our advantage in this case. If the ORM was much better at generating complicated schemas, this would never have worked. So we can use that. We can trick them. And we can use their simplicity to make things work. And it's really about like figuring out, and it took a while to convince the organization that you can use the flexibility of the database to make your life a lot easier. Like you don't need to touch 25,000 classes in Java to make this change. You needed to touch like 5. And then put one trigger function into the database. And then it just worked. So using the flexibility of Postgres in this case, you could do similar things with any database capable of doing a trigger, of course, but the combination of these different features in Postgres makes it so much easier than we've seen in anything else. Like range types makes it a lot easier. The flexibility in how you deal with the search path in Postgres. I'm sure you could rec up something really ugly using a whole bunch of weird synonyms in Oracle to do something similar to that, but search path just makes it easy. So use that flexibility to really don't just treat the database as in the whole stack as a completely dumb storage. Use all the functions that are in there. It'll make the rest of the layers a lot easier. So that's all I had. Any further questions? Yes?
So the one question I had was how did you keep up with the date that a particular report was run so that it was within your range? Because I could see if I create a report and I call and I say the date of the report is now, I guess in the same transaction now is equal. And so
yes.
you have to create the report row in the same transaction as you do the other logic. Otherwise, it wouldn't
yep.
work because the time would.
That is correct. But it does use the fact that now, we're using now instead of clock timestamp for that particular reason that it doesn't change within a transaction. And that's also how we track if you update the same row more than once. We really only store one of those because we use the fact that a transaction has an atomic timestamp. It doesn't exist over time, even though it looked like that when you ran it. Actually, I don't think they ever built a UI that was that sophisticated. They just had to type the time in manually. Because usually someone had printed the report probably and had a timestamp on it. It was sort of at that level. But that's just a user interface feature. It was not accurate then to the millisecond as the database was. It would have been if they typed it in that way and if they printed it that accurate. But again, we had fairly few updates. So I doubt anyone ever really needed millisecond level. They just rerun the report twice with slightly different timestamps. But yeah, we could have done something like that. That's more, it's a user interface thing. At the database level, we could certainly have done that. Anyone else? Yep.
Yeah, when you generated the history tables, you showed that you were able to just do like original table.
Yep.
Didn't you also need to change the keys?
Let me go back. That one? Yeah. So if you just do like with nothing else, it doesn't create the indexes. You have to say, is it like with indexes or something? Including indexes. Yeah, if you say like table 1 including indexes, it would have included indexes. And then, yes, any unique index would have caused a problem. So by default, that one will only copy the columns over. And then you'd create indexes manually. And then, of course, this step over here would create our new primary key. But if there were other unique keys in it, those would have caused a problem if we just copied the indexes over. Okay, anyone else? Okay, then thank you very much for listening.
One observation would be that
Okay.
you have to keep the history table and the time travel table in the same database as the forward-facing, the current view of the data. You might be able to push that over like in some other database.
We kept it all in one. You could push it over and use a foreign table.
Yeah, just for one reason or another. Maybe for auditing reasons.
Yeah, sure. Yeah, no, absolutely. But in that case, you could use a foreign table for that. And you could even use, like, with the new functionality that's coming out in 9.5, you could combine it with a foreign table with like a partition, with one partition living on a different machine kind of a thing. It's all doable. We didn't need to do it. We didn't have that much data. I think the entire database at this point was like 200 gigs or something. So even with quite a bit of history data in the future, it would still not be big enough that we couldn't just deal with it on a single machine. I mean, there's a replication slave for availability, but that's a different thing. Okay.